Good day. We are from Team Sleep Equals False with me, Wong, and my partner, Jason. Now we will be presenting our Milestone 3 on hop, skip, jump attack. So what is a hop, skip, jump attack? So this name is actually inspired by a children's game called Hop, Skip, Jump, involving those movements in the 17th century. This is because the algorithm is there is a jump, skip, and jumping mechanism in our algorithm. So this attack is an adversarial machine learning attack, trying to attack on the current classifiers and models. And it is a black box decision-based attack, which means that we do not need to know the inner workings of the model. We only need its output or decisions from it. So our goal is to fool image classifiers with minimum perturbation where humans cannot perceive the difference. So one application of such attack is in self-driving cars. So if a self-driving car somehow is classifying this stop sign as a go sign with our attack, this will cause quite a serious accident. Here are some features of hop, skip, jump. So it mainly uses gradient estimation at the decision boundary, and it requires very few queries to the model. It also only requires the labels, which is quite realistic, as we normally do not have access to the inner workings of a model. Also, it is still a state-of-the-art attack after years of publishing. This is because it is effective against various existing defenses, and there are only very few research papers to improve it, such as using DCT and modification for probabilistic classifiers. Next, this is how the attack works. So here we have our initial image dot and our target image cat. So this algorithm will add some perturbation and see if this is a dot. And if we are at this point, it still looks like a dot, so it's not good enough. So we move over here. And now the label becomes a cat, which is what we don't want. And then we'll move into here. Now this picture looks almost like a cat, but the label is actually a dog. So we have achieved our goal. And this will be our adversarial sample. And we have two types of attack, which are untargeted attack and targeted attack. For untargeted attacks, we aim to minimize a certain distance metric, which will be explained later by Jason, subject to such that the original label is different from the adversarial label. For targeted attack, we try to minimize that certain distance metric such that the targeted label becomes our design targeted label. So with that, we can define our boundary function, which is the probability, the maximum of the probability of the other classes minus the probability of our target class. And with that, when we obtain this boundary value, we can determine that if this value is greater than 0, that means that we have produced an adversarial sample. If this value is less than 0, then we can determine that that sample is not adversarial. So here is the intuitive explanation of the algorithm. So here in the blue zone is where x is greater than 0, and the red region is where sx is less than 0. So here we have our target point in the blue region and our starting point somewhere in the red region. First, we do a binary search to get to the boundary, a point on the boundary, and then we will use this point to get a gradient using gradient direction estimation. Then we'll select a step size and then move towards the step size, and we'll get the sign through the gradient estimation. After that, we'll use this point to step near back to the boundary point, and this process is done iteratively until it converges. So here is a quick description of gradient direction estimation. So we first add a little perturbation to the image, and then we'll feed the image back into the classifier, and then we will check the label. Based on the label, we can know what is the sign, and then we multiply it with the perturbation. Then we'll sum all the sign perturbation and get our final values. Now I would like to discuss its effectiveness against the existing defense. So here we can see that it has over 86% success rate and 42% success rate against defensive distillation and region-based classification. These two are the more generalized defense methods, and it has achieved a very good success rate on them. However, on adversarial training, specifically trained against this kind of attack, it only has 6 to 11% of success rate. However, this performance is comparable to most attacks, most state-of-the-art attacks. Now I will invite Jason to explain our changes to hop, skip, jump.
Thank you. Can you see my screen? Okay, thank you. Thank you all. Once again, good day. I bid to Dr. Rafal, the tutors, the respected teaching staff, and whoever who is watching this. My name is Jason, and I'll be discussing about the changes we made to hop, skip, jump attack. So as we can see, the hop, skip, jump attack is the state of art attack against many defenses, and we have seen that it has a very good performance against the defenses. So what are the changes that we can make to make this attack more efficient and better? So we have thought of the way is that since the hop, skip, jump composed of a three-part algorithm where it has the boundary search, the gradient estimation, as well as the step size. So we decided that for the boundary search, rather than using a binary search, we will use exponential search instead. So why would we use exponential search? Well, it is based on two observations that we have made while running the algorithm. The first observation is that we found the value from the binary search would gradually approach 1. While another observation is that the number of binary search iteration needed, except for the first binary search, is 16. So 16 is quite a large amount of quite a huge number, and we aim to reduce the searches through exponential search. So this is the observation 1. As you can see for the graph, as the iterations grow, the binary search value gradually approaches 1. As you can see from around iteration 40, the graph gradually approaches 1. While before that is quite random as it goes up and down in certain cases due to the binary search nature. So for observation 2, as you can see that the number of binary search per iteration for the normal hop, skip, jump attack is 16 for all the iterations, in fact. So we aim to minimize this. So our aim is to reduce the number of binary search calls by using the exponential search, which fixes the search boundary of the search range for the binary search. So exponential search can significantly reduce the search range. We do this by setting the lower bound to be the start value, which is an arbitrary value. However, we have chosen that 0.99 is the most suitable value, as we will discuss later, and we will use this start value to be powered by 1, which is the number of exponential search iteration currently. While the upper bound we would choose the previous value of the lower bound. If it is the first iteration, we will choose the number 1 as the upper bound. So this will help reduce the search needed from 16 to eventually 9, which especially at later iterations where the binary value approaches 1, where the number is between 0.99 and 1. However, you may ask that by doing an exponential search prior to binary search may cause incur a huge cost. However, based on our research, we have found that in fact that having the exponential search combined with the binary search, the overall searches needed is still less than the binary search from the normal hop-skip jump attack. So this is our result. Using 20 iterations, which is around 291 iterations, we have found that the starting value, using the starting value of 0.9, we will have a speed up of 3.33%, while using a starting value of 0.99, we will have a 8.4% increase in speed. On the other hand, using the iteration 30, we have found that using the starting value of 0.9, we would have a speed up of 5.41%, while using a starting value of 0.99, we will have a 7.6% increase in speed up. This is mainly due to having less search, as you can see in the table below. So in conclusion, we have found that using the exponential search, we will have a 7 to 8% increase in speed of generating the attack. This is very impactful for long computation, especially in generating the adversary attack, since an attack will take up to 6 to over an hour, depending on the model used, as well as the algorithm, the variation of the algorithm used. This you may say, some people may say this increment is somewhat small, but it is due to the fact that the algorithm is comprised of 3 components rather than 1 component. So increasing the efficiency of 1 component might not influence the speed too much. This proven on the fact on our Milestone 2 findings based on random search, that we have found that even using random search instead of binary search for the algorithm, the other components do in fact actually contribute their part in the attack. So in addition, we have also found that less search is needed using exponential search, which makes the algorithm more query efficient, as it is the aim of the attack originally. Okay, thank you. This is all for our presentation, and this is our reference list. Now we will move. So this is our implementation of the hop skip jump attack in Colab. So first we would we are required to install the required files, which is from the adversary robots toolbox. Next, we will import the required library, which we will use in our algorithm. Next, this is the hop skip jump implementation by adversary robots toolbox. So this is the main attack, and this is where the values are initialized. This function is used to generate the attack. This is the part where they clean the value and ensure the parameters are correct. And this is the part where the samples are generated. So if it is targeted, the parameters would be these parameters. While if it's untargeted, you will have different parameters, and it will call the function preturb. So for preturb, the function generate an initial sample, which will be used in the attack later, which is called by the attack, and which is in this part. So the attack is basically our hop skip jump algorithm discussed by Wong. So the algorithm starts by computing the delta, which will be used in the gradient estimation, and the sample is used the current sample, the initial sample is used for the binary search to find the boundary, and we will use the boundary value to find the gradient and update the value accordingly, which would be used in the step size search next, which we will find the adversarial, the next adversarial example, which will be used in the next iteration. And this goes on until we successfully completed our attack. And this is the binary search which we use, which is the normal implementation of binary search. And next, we define our model. So we basically, our team has chosen to use ResNet 50 as it is quite easy to be used. And the classifier we chosen is Keras. We also get the targeted and initial image. So as you can see, the Keras classifier thinks that this is a koala, and it thinks that this is a notebook. So we will move to the actual attack of the original implementation. So this runs the untargeted attack, where the attack tries to change this image such that it will be perceived by the classifier to be another label rather than its original label, which is a koala. So in this case, we have seen that the image is perceived by the classifier to be a wombat, but in reality, it's a koala. And the attack will goes on until the L2 median error is reduced to be able to fool the classifier more efficiently. As you can see, the next step, the classifier thinks that this image is actually a weasel, and the L2 error is decreased. And next, it still thinks that it's a weasel, and the L2 error is decreased. And this goes on and on until it reaches the final step, which we have seen that the L2 error is around 500, which is quite acceptable, as well as the image is quite clearly seen as a koala, but it's labeled by the classifier as a weasel. So our attack is successful in fooling the classifier. And furthermore, we could either increase the iterations to make the image more refined. This is another implementation we have made, which we changed the binary search to a random search instead. However, this is done for our Milestone 2, and we have found that using random search, that other components contribute equally, if not more, than the binary search in finding the boundary values. So as you can see, the attack still works even for random search. As you can see, it thinks that this is a wombat, but actually it's a koala. And next, it thinks that it's an urban camera and etc. And it will be the same as the targeted attack above. So next, we will move to the targeted attack. So for targeted attack is that we want to fool the classifier of thinking an image is a targeted image instead of a random one in the untargeted attack. So in this case, this is a notebook, but we want to make the classifier to think that it's a notebook, but in fact the image is a koala. So it starts from the image of notebook and it slowly transforms to the image of koala. As you can see, this is the image of notebook. It slowly changes. The L2 error also decreases. It slowly decreases, and eventually the image becomes a koala. But the classifier thinks that this is actually a notebook. It means that our targeted attack is successful. This is the attack for the, this is the same attack. And this is the implementation for the random search variant, which is also similar. However, we can see that due to the random search, the attack is not that successful. As you can see, the images still have some outline of the laptop. However, it still does surprisingly well, even though we are using a random search rather than a binary search. And this is our implementation of the random search for Milestone 2. Most of the stuff are still the same, but instead of binary search, we have opted to use a random search instead, which is this part. Next, we will move to our changes we have made for Milestone 3, which is this milestone. And the stuff the functions are and parameters are normally the same, but what we have changed is in the binary search, we instead opted to use exponential search. So in this case, the exponential search starts here. So our alpha is initialized with a start value, which is given by the user. And if it's not, it's initialized to 0.99, since we have found that 0.99 as a starting value is most suitable. And we interpolate the data, and we check if the interpolate sample is satisfied or unsatisfied. So if it's unsatisfied, it means that we have reached the other side, which is the non-adversarial side of the attack, which means that the search range should be stopped as we have found the boundary. If not, we will continue to find the boundary by using alpha, which is given a power of 2, and the O alpha is taking the previous alpha version. However, the O alpha in this case is the upper bound, while alpha is the lower bound in this case. And this will continue to loop until we find the boundary and the range is found. However, normally the algorithm will not go too many loops in this phase, especially in the later iterations, since that the value is normally between 0.99 and 1, which would instantly go to the binary search, which is this one. And the binary search will do the same thing as the previous implementation. So we have done our analysis on the default hot skip jump, and to discuss why there is a need to have an exponential search rather than a binary search. This is the same thing we have discussed in the presentations and our findings. As you can see, the values are 16 for most of the is 16 for all the iterations, right? As you can see, the number of binary search is 16, and 30 iterations is the same thing, where the attack is successfully carried out. And this is our implementation of exponential search variant using 0.9. So in this case, our attack is still successful. As you can see, the attack is initially is quite blurry, and as it goes on, the number of binary search eventually decrease, and the image will become more clear as well. And the result of the binary search will gradually approach 1, as you can see at the end. For the binary search, this is our final output, which is a koala, but it thinks that it's a neck brace. And the value is, the final result of the binary search is quite close to 1. And the number of search is 12 rather than 16 in the default implementation. This is another of our example. This is for the 30 iteration, which is basically almost the same thing. And we'll move to the next variant, which we use 0.99 as the starting value, which we have found that the decrease in the number of binary search is more significant than before. As you can see, the number of binary search and the bound search gradually decrease, and eventually it will become lesser and lesser until you reach 9. And the bound search will be 2, which is overall still less than the overall implementation. And in this case, the bound search has become 1. And the overall searches needed will be less than the 0.9 starting value variant and the default variant. And the 30 iteration is still the same. And this is our analysis as we have discussed above. And yeah, the speed of the attack is increased and less search is needed. That is all for my part. Thank you very much. Now I will pass the stage to Wong.
Okay, thank you, Jason. So now I will be explaining our results on the attack against the defense proposed by Team Whitehead. So before we begin, let's look back on the original implementation of hop, skip, jump and the results on the targeted attacks. So here, as we have known, the original image is a notebook, and our adversarial sample produced in the end is a koala with a label of a notebook. And then our original image is actually a koala, where we want to fool the model to make it cannot differentiate between koala with the same picture of a koala, but now it will be thinking it as a notebook. So here, in the scenario proposed by Team Whitehead, they actually propose a scenario where in a fully automated shop where there are no workers and there are only AI where it can detect the items checked out by the buyer, and then it will provide the bill. And we assume that there is a model which will be checking the items, and then with their defense mechanism, which is using an explainable AI, specifically line in their case. So they actually prove that the explanation remains secure and convincing when there are patches on the image, such that they can actually tell there are patches on the image and can successfully tell the model that this item has been tampered. So let's see how our attack is against this explainer. Okay. So here we set up the explainer, and now we will just check our original image, the labels and the confidence value. So originally the confidence value is very high, is a koala, but in the per type image, now we have the notebook with the highest confidence value of 0.2. However, surprisingly, koala is still the number three prediction with a 0.13 confidence value. So now we will just see what are the features that are checked by the ResNet 50 model. So here for the koala, it is checking this in the yellow dots around here. So when we overlay these features on the original image, we can see that this is checking around the face and the arms. As for our per top image, now it has become something like this. So while the arm part remains, but there are like more other random features detected around. And so when we overlay it, now becomes different. So does that mean that we have failed to fool the explainer? I think yes, we in fact did not fool the explainer, and the explainer will be able to tell that our image has been tampered. But in our defense, we would like to, the proposed defense model is actually by having a storage where each label has an attached explanation, and then every time when an item is checked, the explanation will be generated and will be compared against the expected explanation. Well, this has a couple of problems. First, it takes a lot of manpower and effort to put each of the expected explanation to each of the labels, seeing that there are so many different labels in the modifier. Even if you only decide to do it for specific items, it still takes a lot of effort with how many items in the store. Next, it also takes a lot of computation effort, since for every item scanned, you need to produce one explanation for it. So it really depends on how fast the explainer can produce the explanation, or else it will be very slow and it will become an inconvenience for the buyers. Therefore, and also against, while facing, as we have proven before, like the adversarial training, if there are any like human intervention for within the security side of things, hop, skip, jump attack becomes much less effective. That's our conclusion for the defense proposed by Tim Whitehead. And that's all, and thank you.